All right, so this is, well, we'll hope it's recording. This is Math 150, Lecture 5. So we're doing equations of planes and lines today. So my cousin Elise unfortunately passed away recently. She was a big Star Trek fan. Any original series Star Trek fans? All right, so you are basically the only one for the cultural extra credit today. Can you name what episode this is from? This is in the handout. And the other one was this one. These were actually considered good special effects back then. All right, so the first is from Balance of Terror. And so in the Balance of Terror, the Romulans are picking off our bases on the neutral zone. And so you have a couple of Federation bases. And a natural question you might ask is, well, we'll have more than this. I think we had at least 7 to 9 bases. Are the bases all in a plane? Or are the bases actually spread out three-dimensionally? Any of you ever see the movie Laser Team? Very bad movie. In the end, they decide to build a wall around the Earth to protect us from attacks of aliens. And people say, well, why don't the aliens just go either above or below the space wall? It's not going to really do much. How would you tell if they're all in a plane? Well, you need to find out the equation of a plane. You would have the coordinates for these, and then you would just figure out, do they lie in the plane? In three-dimensional space, do you think you would want all of your bases in a plane? Well, how thick is the galaxy versus how wide it is? So it might effectively be a plane in three-dimensional space because the galaxy is so long relative to how thick it is. So let's find out the equation of a plane. So if you think about how can you describe a plane, well, the way we described a line was we had a base point and then we had a direction. So I'm going to show you two different ways to represent the equation of a plane. So one is base point plus, instead of a direction, what do I need now?
A normal vector.
Well, that's one way. One way is base point plus a normal vector. So before, I had to go in one direction. Now I have to be perpendicular to a direction. So down here, here's the origin. Here's my point P0. Here's, the normal direction. And then there's the plane of all vectors perpendicular to this. So a way of looking at that is if I had a vector v in this plane with P as my base point, then it would have to be perpendicular to this. And if you think about how many directions we have 3 directions. If I have to be perpendicular to this direction, that leaves me a 2-dimensional space that's going to leave a plane. So let's say V has coordinates x, y, z. Let's say P has coordinates px, py, pz. And let's say N has coordinates nx, ny, and z. So when I say v, am I talking about the distance from P here, or am I actually saying that these are my coordinates, it's this line coming all the way from the origin? If my vector is the vector x, y, z, I'm measuring it from the origin. What I want is, I want the distance, I want the vector from P0 to v. So I look at v minus P0. And that will give me this vector here. And what do we know about v minus P0? What should be true about v minus P0? If v is supposed to be in the plane containing P0 and perpendicular to the normal, what should be true about this vector? So the normal is coming out perpendicular to the plane. Yes?
It's dot product.
It's dot product. Dotted with the normal should be 0. Is it the 0 vector or the 0 number?
The 0 number.
The 0 number. Dot product is going to be a number. So this is one way to get the equation of a plane. So if I look at what's going on now, I have v minus p naught, so that's vx minus px, vy minus py, vz minus pz, and I can dot it with nx, ny, and z. And depending on what book you use, they'll use different notation for the point, they'll use different notation for the normal. It doesn't really matter. I like to use this so I can clearly tell, oh, that's my point, that's my vector where I am. You could, of course, just use x, y, oh, sorry, I'm using x, y, z, not vx, vy, vz. Okay. And this should equal 0. All right, so now if I just go through and do the math, I get nx times x minus px plus ny, y minus py, plus nz, z minus pz equals 0. So you can write this as nxx plus nyy plus nzz equals d, where d is going to be nx px plus ny py plus nz pz, or just the normal dotted with the point p0. I'm just taking all the negatives and just moving it to the other side. So this is our equation of a plane. And you can see here's our generic point x, y, z. Those are its coordinates. I'm dotting it with the normal and x and y and z, and it equals some number. How do you figure out what that number is? Just take any point that's on the plane. So if I take the point x, y, z is the point p naught, I'll get nx x plus ny py plus nz pz. So this is just any point. So the difficulty you have to remember is you want to look at the distance from p naught to your point in space. That vector is what's supposed to be perpendicular to the normal, not the vector from the origin to your point. What point would be wonderful if it went through your plane? If you could choose your plane to go through any point, what point would it go through?
0, 0, 0.
Yeah, it would go through the origin. And if it goes to the origin, what would you choose as your base point?
The origin.
The origin, 0, 0, 0. And then this dot product would just be 0, and you would just get, nxx plus nyy plus nzz equals 0. So that would be the simplest way to do it. Okay? So once we know a normal vector, the rest is not that bad if we have some base point. If I give you 3 points, can you figure out the plane that contains 3 points? So as an exercise, given 3 points, find the plane. So imagine you've got, here's the origin, here's P, here's Q, here's R. And I want to find the plane that goes through P, Q, and R. Any thoughts as to how I would do this? So what 2 inputs do I need if I'm going to find the equation of a plane? Yes? I need a base point. We have 3 natural candidates for the base point, P, Q, and R. And I need a normal direction. Any thoughts as to how I could get the normal direction?
Can we find a vector perpendicular to P, Q, and QR?
Yeah, so if we look at these vectors, the distance from P to Q, that's got to be in our plane. And P to R, that should also be in the plane. So we could say maybe little v is Q minus P, and little w is R minus P. So that will give us 2 vectors. How would you find a vector perpendicular to these 2? You would use the cross product. So you get n would be v cross w. Could you do w cross v? Could you go through the alphabet the opposite direction? Yeah, all it will do is it'll multiply the normal vector by -1. Well, that's not going to change the plane. You always want to think, how important are our choices? Well, if I just multiply by -1, not going to change anything of significance. could I have used Q as my base point and look at P minus Q and R minus Q? Absolutely. Yeah, the algebra might look a little bit different, but I need to get my two different directions. Once I have my two directions, I can find a normal vector. So this is showing us a lot of nice applications of the cross product. It's a really nice way to get that perpendicular direction. Okay, so this is converting the equation of the plane into what we saw before. There is another way to write the equation of the plane. The book I don't think talks about this, but I like this approach as well. And for some advanced mathematics, this is a little bit more useful, and it highlights a little bit more of what's going on. What dimensional space is, okay. What dimensional space is a line? So how many dimensions does a line have? Yes. One. So we should be able to specify wherever we are on a line with just one parameter. You know, just like a curve, a nice curve in space, one parameter. It's a one-dimensional object. How many dimensions is a plane? Two. And so we should have two free parameters. So the equation of the plane, we had some relation involving x, y, and z equal d. So once I know x and y, then z is forced. So it really looks like it's a two-dimensional object. There's a way to make it a little bit more obvious. So here's another plane equation. I'll call this point plus directions. So we have a base point, P0, and we have two directions, call it V and W. So now, here's my point P0, and here's the vector V, here's the vector W, and here's the plane that contains them. So I could look at all things of the form, I'll call it P of ST is going to be P0 plus S times V plus T times W. And this will also give me an equation of a plane. When S and T equals 0, I'm at the point P0. And then you give me any values of S and T, and that just tells you how I move. Yes?
Do V and W have to be perpendicular?
So that was one of the questions I was going to ask. So you've anticipated one question. What would be the worst case maybe for V and W?
They're the same.
They're the same, or they're along the same direction. So if V and W are in the same direction, could this give us a plane? It will give us a very degenerate plane. It will give us a line. So you can argue as to whether or not you consider a line a degenerate plane. I don't really want to have that argument. That's not going to be good. We want V and W to be at least in different directions. The most common choice is to have them perpendicular, and then things are very convenient. But they don't have to be perpendicular. So we could have them, if I have, say, V like this and W like this, I would just be getting something that looks like this. Perfectly fine coordinate system. So depending on the problem, sometimes you want different coordinate systems. I'm moving V units in this direction and W units in this direction. Is this a huge difference from a rectangular coordinate system?
Yeah.
It's different, but is it a huge difference? No. It still looks roughly, it's at least parallelogramish. So I would say it's not a big change to go from something like this. Okay? And there are times when this is more convenient. So what I want to do now is I want to shift to the big coordinate systems, the polar coordinates, the cylindrical coordinates, the spherical coordinates. These are the big three coordinate changes. Okay? The polar is a little bit harder because of the name. What do you think cylindrical coordinates are good to study? Cylinders, yes. Every now and then we have good names in math. What do you think spherical coordinates are good to study? And what do you think polar coordinates are good to study? Circles, okay, so yeah. What is secant? Who knows their trick? What is secant?
1 over the cosine of theta.
1 over the cosine. Does that bother anybody that secant is associated with cosine and cosecant is associated with sine?
Makes me very angry.
It makes me angry as well. And unfortunately, I do not have enough mathematical clout to do anything about that. We are stuck with that. There may be a good reason why we are stuck with that. I don't know. I've never really looked. I've just been too upset and angry. Sometimes you are forced to have bad notation. Sometimes the notation is good. Cylindrical and spherical are good names. Now, one of the problems is the physicists and the mathematicians have different notation for spherical coordinates. And I learned the notations essentially at the same time, 2 different ways. And I will often slip and use the physics notation and not the math notation. And so I will try to use the notation that the book uses. Does it matter which notation I use? No, but you need to be consistent and you need to be aware. So frequently you have to look at books and see, where is this book from? Who are my physics students? The worst equation I ever saw in a physics book was P equals mf. Anybody know what equation that is?
Newton's second law.
This is Newton's second law of force equals mass times acceleration. This was the worst notation I've ever seen. You're allowed to write Newton's second law like that. You just need to be very careful and aware. Polar coordinates. So how many of you have seen polar coordinates before? How many of you have not seen polar coordinates? Okay, everyone, okay. So we have x is r cosine theta, y is r sine theta, r is the square root of x squared plus y squared, and theta is arctangent of, so here's r, here's x, here's y, here's theta. It's arctangent of y over x. Sometimes people write this as tangent inverse of y over x. The reason I prefer arctan to tangent inverse is it's not clear sometimes, is this the inverse tangent or is this 1 over tangent? And that's why we actually use things like arctangent to make it really clear what we're talking about. So the point of coordinate systems is to try to make your problem look nicer. And if you have things in one coordinate system, you should have the ability to express things in another. How many of you have ever traveled to another country and had to convert money? Okay. You give the currency people your money and they give you back money in the other currency, modulo a small transaction fee. Or sometimes not necessarily a small transaction fee. But in the idealized world, you would just convert your money directly to the other currency. And if you multiplied your money by 5, you'd get 5 times as much of the other currency. A good coordinate system, a good transformation, if I tell you what it is in xy space, you know what it is in r theta space. Or if I tell you where you are in r theta space, you know what you are in xy space. Is there any point here in xy space where you don't necessarily know your r theta coordinates? Is there one point where you've got to be careful? Yes?
Where x is 0?
Well, so it's a little bit more than just x is 0. It's not just x equals 0. It's x and y is 0. So if x and y are both 0, you're at the origin. So your r is 0, but what's your theta? If x is equal to, say, 1 and y equals 0, it turns out that we will get an angle of 0 and a radius of 1. So the coordinates will still make sense. The only place the coordinate transformation breaks down is at the origin. So note x equals 0, y equals 0, goes to r equals 0, theta is free. So this is a little bit bad, is we have infinitely many choices of theta that correspond to the same point. So the coordinate transformations break down here. Fortunately, they don't break down too badly, and it's only at one point, so everything will be okay. but it's worth being aware that coordinates break down. Okay. In Cartesian space, we can write down what's the equation of a circle. So a circle is x squared plus y squared equals 1. What does a circle look like in polar? What would that circle look like in polar coordinates?
Would that just be r squared equals 1?
Almost. Yes.
It'd just be like r equals 1.
It's just r equals 1. So you always want to think about what is the domain. So here, for the domain for polar coordinates, we will always assume r is greater than or equal to 0, and we'll assume 0 less than or equal to theta less than 2 pi. Because if you have r as both positive and negative, I can change things by just changing theta by 180 or by pi radians. So we'll always assume r is non-negative. We'll take the positive square root. And we'll assume theta is between 0 and 2 pi. If we allowed theta to go all the way up to 2 pi, then we would lose uniqueness. And this will cause some slight issues that real analysis can remove without too much trouble. So the equation is very nice in polar coordinates. Have you ever looked at what a circle looks like in the plane? Yes, all the time. It's a circle. With some imagination, that's a circle. What does a circle look like in polar coordinates? Well, here I'm graphing it in xy space. I want to graph it now in r theta space. What does a circle look like in r theta space?
It's a line.
It's a line. R equals 1. So here's 2 pi. That's a circle. That's what a circle looks like in polar coordinates. Now, we talked a moment ago when we went to V and W weren't perpendicular. And I said, is it a huge deal? Does it look fundamentally the same? It's still parallelogramish. Does this look fundamentally different? A circle now versus a straight line. I would say here there's a real difference now in how they look. Which do you think is an easier object to work with, a line or a circle? A line. And this is one of the powers of these change of variables. Let's look now not at a circle, but at a disk. So the disk would be x squared plus y squared is less than or equal to 1. That would be the unit disk. So it would look like this in xy space. Right? I'm pretty sure the book does not have these pictures. This is the value added. What do you think a disk looks like in polar coordinates? So this was x squared plus y squared is less than or equal to 1. What would the equation be in polar coordinates? What does this become in polar coordinates? Yes.
R is less than or equal to 1.
So this becomes r is less than or equal to 1. So what will this look like in polar coordinates?
A rectangle?
It'll look like a rectangle. Which do you think is an easier shape to work with, a rectangle or a circle? Rectangle. This is the whole point of converting things to polar coordinates, is we're going to eventually do integration. In calculus, it's very nice and relaxed. Calc 1 is differentiation, Calc 2 is integration, Calc 3 is both at a breakneck speed. So we're going to integrate, we'll have two integrals to do. If I'm integrating over a disk, oh Lord, this is going to be annoying. If I want to figure out how far x goes, okay, x goes from -1 to 1, and y goes from negative the square root of 1 minus x squared to positive the square root of 1 minus x squared. So if I want to integrate over a disk, it would be like x goes from -1 to 1, integral y goes from negative square root of 1 minus x squared to the square root of 1 minus x squared. These should not look like fun bounds of integration. In the polar version, r goes from 0 to 1, theta goes from 0 to 2 pi. Much, much easier. So this is why we convert things to polar coordinates. Okay? And now all you have to do is whatever problem I give you, you just go through and these are the substitutions. So x is r cosine theta, y is r sine theta. And the reason this is coming from is if I have my right triangle, here's my angle theta here. Here's r, so this is just r cosine theta, and this will just be r sine theta, just by classic trick. Okay? Right. Any questions about the basics of polar coordinates? What do we do for cylindrical coordinates? What's the difference between cylindrical coordinates and polar coordinates?
Z equals Z.
Z equals Z. Z is just along for the ride. So if I want to go from polar to cylindrical, all I have to do is just add Z equals Z. And this is ideally suited for problems that have great cylindrical symmetry. There are many different approaches you can take to teaching Calc 150. You could do a very geometric approach, drawing lots of curves, drawing lots of regions. I prefer not to take that approach. I prefer to take the approach of actually applying the math to solve problems. So one of the problems we'll be solving is we'll be using multivariable calculus to model Major League Baseball. So here, if I had a cylindrical shape, basically we're saying it has slices that look like circles. If you've taken physics and you've seen like parabolic mirrors, you maybe might have something like z equals r squared or something like that. And you can start to see what would these shapes look like. So I strongly encourage you to use a program like Mathematica to look at these. Okay. Any questions on the cylindrical? So you can see how much time I really want to spend on cylindrical. Okay. I really want to spend the rest of the time on spherical and then talk a little bit about level sets. Okay. How many people have seen the original Star Trek series? Okay. So the other episode was from, the first episode with the Romulans and the Federation bases was from Balance of Terror. The second one showing the giant sphere was from the Corbomite maneuver. Any James Bond fans here? Oh, this is sad. All right. There goes the Goldfinger reference. Okay. Spherical coordinates. So I've got to be very careful. I want to match what the book does. So here's the x-axis. Here's the y-axis. Here's the z-axis. And I believe they use phi as the angle coming down from the z-axis. Okay. Your book uses phi? Yeah. Okay. I learned it first from the physicists. They use theta coming down. It makes sense to use phi, not theta, or even better to just use theta 1, theta 2. The reason this is better notation than what I learned is you always want to reduce a new problem to a simpler problem you've already studied. When you see spherical coordinates, what coordinates does this kind of remind you of? So what kind of coordinates would be similar to spherical coordinates?
Polar.
Polar. So in polar coordinates we had an r and we had an angle theta. So we're going to use rho to represent our distance here. So for spherical, we'll have rho is greater than or equal to 0. We'll have 0 less than or equal to phi is less than or equal to pi, and 0 less than or equal to theta less than 2 pi. And the idea is we want coordinates so that we see the polar coordinates lurking in, living inside. And if you look at what's going on, if I come down phi from the z-axis, now I can figure out exactly what my z height is. Z is just going to be rho cosine phi. So does everybody agree that if I come down phi from the z-axis, that the height is just rho cosine phi. The maximum would be if I come down nothing. And what's cosine of 0? The minimum is if I go all the way down 180, in which case I would get negative rho. And if I come down pi halves, I'll just get 0. If you think about trying to write the equations of points on a sphere, if I come down, I can then spin 360 degrees or 2 pi radians. And I want to be able to get every point on the sphere once and only once. Do I have to go, if I'm coming down from the z-axis, I come down, here's 90 degrees, 180 degrees. Do I have to go all the way back up to the top? No, because if I'm spinning, there's no need for me to be coming back up to the top. Once I've come down over here, I can just spin around to get to that point. So because I allow theta to go from 0 to 2 pi, I don't need phi to go from 0 to 2 pi. If I did, I'd cover points twice. Once I come down here, I now get all the points at that height. And this is where we begin to talk about level sets. We can look at all the points that have the same z, the same height. And so I just need to come down 180 degrees. Because I'm spinning 360 degrees, I get every circle at that level. If you slice the sphere, you're just going to get a collection of circles. All right, well, if I come down phi, the z height is going to be rho cosine phi. So I can look at what the angle, at what the length is going to be in the xy plane. What do you think its length is going to be in the xy plane? If it's rho cosine phi here, what do you think this length is going to be? So if I look at what's going on in the xy plane, what do you think this length is going to be?
Just the length of the vector.
Well, but remember, I no longer have the full vector. I can write this vector as some part coming up in the z direction, and then some part parallel to the xy plane at that height. So I've got what kind of triangle do I have? I have a right triangle. I love right triangles, right? If this whole length is rho, that's the length of the vector, and this is rho cosine theta, I'm sorry, cosine phi, what do you think this vector would be here? What do you think its length would be? Rho sine phi. So this length would be rho sine phi. And because we want this to look like polar coordinates, what do you think we should call rho sine phi? That would be, in polar coordinates, what would that be?
R.
That would be our r. And now here's our angle theta. So this over here would be r cosine theta, and this would be r sine theta. But we just have to remember that r is actually rho sine phi. Should you memorize spherical coordinates?
A little bit.
Try a little bit more. Yes, yes, Professor Miller, we should memorize spherical coordinates. Right? There's not that many coordinate systems. It's the big three. Who are the big three colleges? I'll ask you, who are the little three colleges? Yes?
Williams, Amherst, and Wesleyan.
Yes, and the big three? Harvard, Yale, Princeton. So there's not that many to learn. You should remember them. Okay, you should remember spherical coordinates, cylindrical coordinates, and polar coordinates. If you forget, you can derive spherical coordinates like this. And I will admit I often have to rederive spherical coordinates, partly because I don't know which way is phi and which way is theta. You can see why they want to keep theta for the plane. Theta is always going to be how much you're moving in the xy plane. And the rho cosine phi is just telling you how much you've shifted upwards. So you get x is equal to rho sine phi cosine theta. Y is rho sine phi sine theta. And z is rho cosine phi. And if you do some algebra, x squared plus y squared plus z squared equals rho squared. So if you just square things, you see everything has a rho squared. sine squared phi, cosine squared theta, sine squared phi, sine squared theta, cosine squared plus sine squared is 1, then sine squared plus cosine squared is 1, you just get rho squared. Okay? In Cartesian, x squared plus y squared plus z squared is less than or equal to 1. What kind of object is that? X squared plus y squared plus z squared is less than or equal to 1. What kind of object would that be in Cartesian?
It's a sphere.
It's a sphere. What's the radius of the sphere?
1.
1. If I did x squared plus y squared plus z squared is less than or equal to 4, it would be a sphere of radius 2. Anybody remember the volume of a sphere? 4/3 pi cubed. Anybody remember the surface area? All right, let me just do an aside. So let's do a circle. What's the area of a circle? Come on, fast, fast, fast. Area of a circle. Radius r.
4/3 pi r cubed.
Circle! Pi r squared. And the perimeter. Anybody notice anything?
The perimeter is the derivative of the
Ooh. So sphere, volume, surface area. The volume is 4/3 pi r cubed. Anybody remember the surface area of a sphere? Or want to take a guess now?
4 pi r squared.
It's 4 pi r squared. Coincidence or deep math? Or at least useful mnemonic? So there is a reason why the derivative of the volume is the surface area. There is a reason why the derivative of the area is a perimeter. This is one of the reasons why I'm trying to teach the class like this and have things flipped. I want to have time to talk about stuff like this. I want to have time to show you the connections. I want to go back and say, this is the equation of a sphere. X squared plus y squared plus z squared less than or equal to 1. What do you think a sphere looks like in spherical coordinates? So what would be the equation of a sphere in spherical coordinates? Yes?
Rho equals 1.
Yeah. Well, not quite rho equals 1. I want the solid sphere.
Rho is less than or equal to 1.
Rho is less than or equal to 1. Basically, it's saying, doesn't matter what theta is, doesn't matter what phi is. A solid sphere means you go at most 1 unit away from the origin. Solid sphere radius 2, go at most 2 units away. What kind of object do you think this is going to look like in rho theta phi coordinates?
It's going to be a line.
Nope, not a line.
a rectangle.
Not a rectangle, you're getting closer.
A plane.
I'm sorry?
A plane.
Not a plane.
A cube.
So is the cube, does all the sides have the same length? If yes, then you're wrong, but you're close. It's not a cube, it's a rectangular box, right? Because theta is going to go from 0 to 2 pi. Phi is going to go from 0 to pi. So these two sides clearly can't be the same length. And then rho is going up to 0 to 1. So in spherical coordinates, it's going to look like a box. Which would you rather work with, integrating over a nice box or integrating over a sphere? If I want to integrate over a sphere in Cartesian, I would have x goes from -1 to 1. And then once you specify x, what would be the range of y? Y would go from the square root of 1 minus x squared with a negative sign to the square root of 1 minus x squared with a positive sign. And then z would go from negative square root of 1 minus x squared minus y squared to the square root of 1 minus x squared minus y squared. That's terrible. Whereas in spherical coordinates, it would be Rho goes from 0 to 1. Theta goes from 0 to 2 pi. Phi goes from 0 to pi. The basic idea when we get to integration is you would much rather have a nice region and a bad integrand than a nice integrand and a bad region. And we can integrate over lines. See, in one dimension, it's really hard to see what's going on, because when you integrate, what's the only region we can integrate over in one dimension? What do all regions look like? You only integrate over one shape in one dimension. A line. We integrate from A to B. It's not that much I can give you. We can integrate from 1 to 5. We can integrate from 1 to infinity. We can integrate from -2 to 5. They're all line segments, or unions of line segments. But once we get up into 2 dimensions and 3 dimensions, then shapes become more interesting. There's actually a difference between 2 dimensions and 3 dimensions. And we'll talk a little bit about what happens there later. All right, so we've been talking mostly about equations, and we did equations of planes. We did the different coordinate systems. For the last 5 minutes, I want to talk briefly about level sets. So the whole point of level sets is just talking about places that have the same value. So if I have a function, the level set of value C is going to be all inputs that output C. So the level set of f of value C is all inputs sent to C by f. You have seen this numerous times. How many of you have looked at a weather map of the United States? And you might see places that have the same temperature. That would be a temperature level set. Do you know what word they use for level temperature? Isotherms. So temperature would be isotherms. If it's pressure, it's isobars. Those would be all places of the same pressure. If you look at, we live in the Purple Valley. You can look at all places that are a certain height above sea level. And if I give you some kind of mountain range like this, if I choose this as my levels value, okay, I would get maybe these points here, these points here. I would miss everything over there. And so these would be the points that have the same level. If I give you a sphere, there's a lot of different ways of writing a sphere. So consider z is the square root of 1 minus x squared minus y squared. And I'll go, so if I look at this, as long as x squared plus y squared is at most 1, this is well defined. And this will give me a height. What kind of object do you think this is? Z equals the square root of 1 minus x squared minus y squared. What kind of object do you think geometrically is this?
Sphere?
Almost. Sphere is a nice whole object.
Donut?
No, it's close to a sphere, but does this have negative z's? So it's not a full sphere, it's a half sphere, a hemisphere. So this is a hemisphere. It looks something like this. And then what I can do is I can look at what would be the level set of, say, f of xy is the square root of 1 minus x squared minus y squared. So for example, what's the level set of f of xy equals say f of xy equals 4/5. What kind of shape do you think that would be? Yes?
Plane.
Well, it's not a plane because it's got to be places where x and y are defined. So here's my function, and I want to look at all inputs that evaluate to a height of 4/5. So I'm basically saying I want my height z to be 4/5. So I want 4/5 equal the square root of 1 minus x squared minus y squared. Yes?
It's going to be a circle.
It's going to be a circle. And so if I square both sides, I get 16/25 equals 25/25 in the interest of time minus x squared plus y squared. So if I bring this over, I get x squared plus y squared equals 9/25. So x squared plus y squared equals, after you do the algebra, 3/5 squared. So not only do we know it's a circle of radius 3/5. So level set is a circle of radius 3/5 and height 4/5. Okay? It's just a circle above the xy plane. So all we're really going to need for level sets is it's just a convenient way of collecting all points that have the same value. I think freshman housing, how many of you are in a building that have, I guess other than the JAs, have somebody other than a freshman in it? So basically in your buildings, everybody's a freshman except for the JAs. It's almost like a level set. If you look at just the age of the people living in it. So we want convenient ways to collect all points that have the same value. And so if you look at the equation of a sphere, x squared plus y squared plus z squared equals 1, we're looking at the level set x squared plus y squared plus z squared equals 1. The level set x squared plus y squared plus z squared equals 4 would be a sphere of radius 2. So the level set is just a convenient way of collecting things. So we'll continue on Wednesday. We'll start looking at applications of stuff like this. Okay.